Next bit of polynomials, and we've seen this a couple of times already, of course, because we saw it in 2 unit with just the quadratic polynomial. Then we saw it in the 3 unit part of polynomials as well, and we're going to look at it yet again with the extension 2 part. That being, if we've got any polynomial, then we know some of the roots 1 at a time. I can always go minus b on a, 2 at a time c on a, 3 at a time minus d on a, and of course this pattern just keeps repeating. If I had 4, so 4 at a time e on a. If I had 5, then it would go minus, what am I up to? F on a, and so on and so on. Other ideas. Fairly common sort of a question, the sum of the roots squared. But we know we can rearrange our perfect binomial, the alpha plus beta all squared, to come up with that expression. So it's the sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. That pattern also carries through. And the reciprocal one's another reasonably common sort of a question that we have. So 1 on alpha plus 1 on beta, I guess best treated like an algebraic fraction, and then you usually end up in the fraction with product of the roots on the bottom and then sum of the roots in some combination, whether it be 1 at a time, 2 at a time, depending on the question. So to generalise, doesn't matter how many roots we've got, sum of the roots 1 at a time squared will be the sum of the roots 1 at a time all squared minus 2 times the sum of the roots 2 at a time. It's very hard to generalise the reciprocal one, because if it's a quadratic, then it'll be sum of the roots 1 at a time over alpha beta. If it's a cubic, it'll be sum of the roots 2 at a time over alpha beta gamma. If it was a quartic, then it would be 3 at a time. So I guess a clumsy way of saying is sum of the roots 1 less at a time than the polynomial over the product of the roots. That sort of idea crops up. Let's have a look at some questions. So we've got a cubic. And if they're nice, mind you, in extension 2, I think it's reasonably rare we get these sort of gift questions. Find 1 at a time, 2 at a time, 3 at a time. So let's find our basic ones. Oh, look at that nice pattern, 2, 3, 4. And so we can, go and do other problems. There's our sum of the roots squared. So again, to emphasise, 1 at a time all squared minus 2 times 2 at a time. So subbing in 2 squared minus 2 times 3, so we get negative 2 for that one. What happens if they wanted cubed? Now, I guess we could come up with a similar expression like we do for squared, where I could go alpha plus beta all cubed, expand it out, and then move the alpha cube plus beta cube plus gamma cube to one side, and I'd come up with an expression that I could sub in. That would work. But there's a neater way of doing it, because it is a cubic. Now, if alpha is a solution, then when I substitute it in, I know the answer will be 0. So alpha cubed minus 2 alpha squared plus 3 alpha minus 4 is 0. Well, beta is a solution as well, and so is gamma. So they would all be true. So I could create simultaneous equations. And what I get is sum of the roots all cubed minus 2 times the sum of the roots squared plus 3 times the sum of the roots 1 at a time, and minus 12 equals 0. And I can sub in each of those expressions. And so basically, it takes the form of the actual equation. The only thing we have to be careful with is the constants. Because you'll notice I've got minus 12, not minus 4. Now, that happens because we're finding the sum of the roots cubed. I'll just finish off this question and then we'll see what happens when it's to the power of, I think I did 4 next. So, okay, let's sub in what we've already found. And, once again, the answer's 2. So if it was to the power of 4, okay. We already said alpha cubed minus 2 alpha squared plus 3 alpha minus 4 is equal to 0, because alpha is a solution. So if I multiply both sides by alpha, it's still going to be correct. So essentially all I'm doing is adding 1 to the power. But I could have done that with beta, I could have done that with gamma. In fact, I wouldn't even write that step. I'd jump straight to that step. Yeah, because essentially it's the equation. So it's copying the equation, but notice now I don't have minus 12. I've got minus 4, the sum of the roots. So the only reason that it went to minus 12 before is because it was a constant. Once I've multiplied both sides by alpha or beta or gamma, it's no longer a constant because I've got that alpha, beta, the unknown. So when it's to the power of, I guess, the order of the polynomial, then we'll multiply the constant by whatever that order is. Otherwise, we just leave it. In this case, it's minus 4. And we just add 1 to the power. So a constant would be the power of 0. Add 1 to the power, we get power of 1. So it mimics the equation. And then I can rearrange it. I guess the only disadvantage with this is that in order to work out to the power of 4, I need to know power of 3, I need to have worked out power of 2, and so on. So let's sub in what we've found. And there we go, it's not 2, it's 18. Yay! I don't think I did the sum of alpha to the power of 5, but if we wanted to work that out now, using that same idea, I could come up with an expression, and it would be the sigma alpha to the power of 5 minus 2 times the sum alpha to the power of 4 plus 2 times sum alpha cubed minus 4 times sum of alpha squared. So in this case, just adding 2 to the power each time. Alpha plus beta, alpha plus gamma, beta plus gamma. Is there a way of doing this without expanding this whole thing out?
Yes.
Well, actually, the answer is no. Still going to have to expand out, but before I expand out, I'm going to do something different. Well, what I'm going to say is alpha plus beta is alpha plus beta plus gamma minus gamma. We've worked out the sum of the roots one at a time. The only reason I do it is because now I don't have 2 pronumerals, I've only got 1 pronumeral there. And I'm still going to have to do that sort of expansion of 3 parentheses. But when I expand this one out, there's going to end up less to substitute into and factorise and things like that. So that's the only reason I do it. You could expand this whole thing out, but there'll be a bit more algebraic manipulation to get it in terms of things that we know. So let's sub in what we know. 2. We have got a quartic. It's monic. Suppose the equation has a root in the form ki. K is real, and it's not equal to 0. I guess this one, hopefully, fingers crossed, is the gift mark of the question. State why the conjugate is also a root. See, they've told us A, B, C, and D are all integers, so we know the coefficients are real. Solutions will appear in conjugate pairs. So if ki is a solution, so is minus ki. So that's all they're really looking for there. So something like that. Roots appear in conjugate pairs when the coefficients are real. Now we're going to show that C is equal to K squared A. Well, I suppose there's different ways of doing it. The way I approached it is I thought, well, why did they tell me Ki was a solution? Maybe that's some sort of hint on how to approach this problem. So if Ki is a solution, minus Ki, I know that's 2 of the factors. Leaves me with a quadratic. I know that quadratic's going to be monic, because the overall equation is monic. So I've called it x squared plus px plus q. When I expand all that out, there's what I get. And I can now equate coefficients. Probably could have done a similar thing by just going, now that I think about it, I could have gone sum of the roots one at a time is minus a. And so ki plus minus ki, that would have cancelled out. And then the 2 other, anyway. I probably could have ended up with the same sort of thing that way. But I've ended up with these 4 when I equate those coefficients. I know that P is equal to A, Q plus K squared is equal to B, K squared P is equal to C, and K squared Q is equal to D. We want to show C is K squared A. What have I got so far? There we go. Yeah, if we combine 1 and 2 together, we've got that. So all right, combine that. Oh, sorry, it's 1 and 3, not 1 and 2. 1 and 3, we get K squared A is equal to C. Next one, show that C squared plus A squared D is equal to ABC. Well, in the second one, I had that Q was equal to B minus K squared. Subbing that into 4, K squared, B squared minus K squared equals D. I've got to get rid of the K's still. So, I've got B K squared minus K to the power of 4. What else have we got? Oh, hang on a sec. K squared, in that last one, we said, what was it? C was equal to...
K squared.
Yeah, so I could rewrite that and say K squared is C on A. That gets rid of the k's. Hopefully now, I've only got a's, b's, c's and d's. I should be able to rearrange this and get what they're looking for. So, multiply by a squared. Oh yeah, rearrange the terms. There's my expression. It's a lot of just algebraic manipulation, really. If 2 is also a root in the equation, so we now know ki is a root, minus ki is a root, 2 is a root. So there's now only one thing we don't know, one root we don't know. B is equal to 0. We're going to show that C has to be an even number. So that fourth root I don't know, I'm just going to call it alpha. The other 3 roots are integer multiples, because k was an integer, remember. So when we multiply the 3 roots together, 2 ki minus ki, it's going to be an integer, whole number. And the sum of the roots is also an integer. So therefore the fourth root must be an integer. Because if the other 3 roots are all integers, add them together and I get an integer, then the fourth one must have been an integer as well in order to keep it that way. So I know alpha is going to be an integer. There's the sum of the roots 2 at a time. I've got some cancelling there. So minus 2 ki and plus 2 ki, they're going to cancel. The alpha minus ki, and that's going to cancel as well. I'm left with k squared plus 2 alpha is equal to 0. What are we trying to show? C is even. There's no C there. Well, k squared is minus 2 alpha. But hang on, C was equal to k squared A. Alright, so I know k squared is a factor of C, which has a factor of 2, therefore 2 must be a factor of C. I could say C is equal to minus 2 alpha A, if I want to substitute in for k squared there. Or I could say that's 2 capital M, where M is minus 2, no, it's not minus 2, minus alpha A. And again, we said alpha was an integer, A was an integer, so therefore M is an integer. So yep, it's 2 times some integer, got to be an even number.
No way. Right.